Hello everybody, welcome to the afternoon session of our webinar. Today I will show you how to simulate laser scanning systems in VirtualLab Fusion. Before we start, I would like to introduce myself. My name is Stefan Steiner and I'm optical engineer at Lighttrans. Here you can see my email address and the address of our website. Before we start, if you have questions during the webinar, please click the raise your hand button and type in the question in the questions window. And I will try to answer the question during the webinar if it's related to the topic, or I can answer it after the session. And after the webinar you have also the possibility to ask the question by using your microphone. And I will record this webinar, and in some days you will find it on our YouTube channel. And all the documents I will present today you find in the download section of our homepage. And just go to the browser, and this is our homepage, and just go to download, documents, and then enter the specific keyword, for example laser scanning, and you will find the related application examples. So, as I mentioned, today I will talk about laser scanning systems in VirtualLab, and at first I would like to show you some basic setups which contain different configurations like single or dual scanning mirror setups, and we will use ray tracing to visualize the light path in the setup. And afterwards I would like to show you how to evaluate the performance of these systems by calculating the field curvature and the characteristic distortion. I will tell you later on what this means. And we are going to calculate the field distributions on the target screen by using physical optics propagation, and we will evaluate the beam shape and the beam parameters of this field distribution. And at the end I want to show you a more complex example where we can investigate the speckle pattern generation on the human retina. So at the beginning I want to give a short introduction to laser scanning systems, and then we jump right into VirtualLab. So nowadays laser scanning systems are used in a wide range of very different applications, and these applications contain the creation of images, for example, like in laser projectors and so on. But they are also used for light detection and ranging purposes, and this is for the measurement of distances and velocity of objects. And the basic functional principle is the controlled deflection of laser light. And by using a laser scanning system, the controlled steering of laser beams is provided. And there are different setups which provide this controlled steering, and two setups I want to show you here. We have on the one side we have some micro mirror module. It's a micro electromechanical scanning system, and another example is this commercial dual axis galvanometer scanner, which contains two mirrors, two deflecting mirrors which can be tilted. So we have these two basic setups I want to discuss today. On the left side we can see a sketch of a laser scanning system with one scanning mirror. So we have one deflecting mirror which is fixed, and the scanning mirror is tiltable along two axes. And this is the model of this micro mirror MEMS module. On the right hand side we have this dual scanning mirror system where we have two scanning mirrors which can be tilted along two different axes, and this is the model of the commercial galvanometer scanner. So at first I would like to show you the basic setup of the single scanning mirror example, and therefore we jump right into VirtualLab. And I've loaded already the example file, and I think most of you are already familiar with the interface of VirtualLab, so we can just discuss the example. So we have here the light path view, where you can find all the components of our setup. We have here the light source. This is a laser diode, which is assumed as a Gaussian wave, and by double-clicking this element you can enter the preferences of this light source and enter some parameters you would like to or you need to simulate. For example, on the spatial parameters page you can enter a waist radius or a divergence angle and so on. You can also change the lateral modes. On the spectral parameters tab you can enter the wavelength or add additional wavelengths and so on. So you have a lot of options to configure your light source. And it's also possible to load and measured beam profile. Therefore we have a stored complete field component, and a measured field can import into VirtualLab by using an ASCII on a bitmap file. So you can also simulate this light path for your own light distribution. The next element is the fixed deflecting mirror. I've shown you on the slide before, and we just enter it. It's a so-called single optical interface, and we have a glass substrate fused silica, and this glass substrate is coated by a silver layer, which is protected by an additional fused silica layer to prevent it from getting dull. And this mirror, deflecting mirror, is tilted by using the Basal positioning, and what Basal positioning mean I want to show you on the next slide. But before, I will want to show you the scanning mirror. This scanning mirror is a micro mirror, and therefore it consists of a metal plate, and this mirror is also tilted by Basal positioning. And after the two mirrors we have a screen. So what means Basal positioning? Basal positioning means if we have an original system with no tilt, the optical axis goes right through the setup. And if we use the Basal positioning, for example, to tilt the lens in the middle, the whole, all components after this lens are tilted in the same way. This means that the optical axis is tilted along this basal orientation of the lens. On the contrary, if you use the isolated tilt option, just the lens is tilted and the optical axis remains constant like in the original system before. So this means that we use the basal tilt setup to configure the initial laser scanning system, and for the scanning procedure we're using the isolated tilt settings. So next I want to show you the visualization of the light path in a three-dimensional view. So we just go back to VirtualLab and go to the light path editor and select the ray tracing system analyzer and just click go. And VirtualLab now calculates us a three-dimensional view where we can see and analyze the light path in our system. And we can zoom in here, and here you can see the plane of our light source, the laser diode. Here is the deflecting mirror, the scanning mirror, and the large red rectangle is our screen. And as you can see, for the initial setup where we have just the basal positioning, we hit the screen just in the center position. And yeah, we can just move it a little bit, and yeah. So what we can do now is to add just in isolated positioning by entering the position tab, isolated, and now for example we can add 10 degree tilt for the angle alpha, okay, and then to see the effect we use the ray tracing system analyzer again and just click go, and now you can see that the beam is deflected along the y-axis on the screen. And this means our laser scanning system already works, and now we can do a whole scanning procedure, and for this purpose we use the parameter run feature of VirtualLab, and we open a new parameter run document by clicking the button in the ribbon above, and here's our parameter run, and now we can select from the table the parameter we want to vary, and I just scroll down to the scanning mirror, and here you can see the isolated angles we want to vary. You can also enter a keyword in the field above, just enter for example Cartesian, because we have a Cartesian angle definition, and activate these two fields, and now we, for example, we can vary the tilt angle from minus 20 degree to 20 degree in 11 steps, and again from 20 degree to minus 20 degree to 20 degree in 11 steps, and doing scanning mode. Okay, and in this table you can see all the iterations that will be calculated by VirtualLab. Just click next. Now we're choosing the ray tracing engine because we want to use the ray tracing simulation engine, and we deactivate the system analyzer because we don't want to see the three-dimensional view. Just click go. And now VirtualLab calculates the single rate distributions of each iteration step we've entered before, and when the calculation is finished we use the combined output feature to create a combined rate distribution. So just go to rate distribution here and just double click, and here you can see our created scan pattern. And as you can see, this scan pattern is not equidistant because the tilt angles are show some nonlinearity, which is caused by the three-dimensional law of reflection, which we did not recognize. And therefore these spots are not in a uniform grid. And to get the uniform grid, we can, for example, use the so-called parameter coupling feature of VirtualLab, which you can find in the ribbon above again, and click Edit and start the parameter coupling. And what we want to do now is, instead of varying the tilt angles, we want to scan to a certain position on the screen. So, and for this position we want to deflect, where we want to have the light, we now need the tilt angles for the mirror. So we choose, in the first tab we choose the parameters we want to set or we need for our calculation. So we use all the deflecting angles for our scanning mirror. We need the basal positioning angles and the isolate positioning angles. Then click next, and now we create a variable for our scanning position XY on the target screen, and clicking Edit, and here you can enter some code to calculate the necessary tilt angles from the desired scan position on the screen. And in this field you have the variables. In the field below you have all the information from the light path diagram, and by calculating and by regarding the three-dimensional law of reflection, we can calculate the necessary angles. For example, for a scanning position 50 millimeters in X and Y, click next, you get, for example, this tilt angles. And to show you that this works, I start a new parameter run, and now we vary the scanning position X and Y on our screen, for example 20 millimeters, minus 20 millimeters, 20 millimeters, and the same in Y direction, again 11 steps for each direction, and using the scanning mode of this parameter run, just clicking next, again choosing ray tracing as simulation engine, next, and go. And due to the fact that we now scanning the light at certain positions on the screen, and if we have calculated the tilt angles correctly, we now get a uniform equidistant grid on the screen. Again, I use this combined output, choose ray tracing distribution, and double click here, and you see we're getting this nice equidistant grid. So what I have shown you in the first example is we have investigated a very basic setup, and we've calculated, I've showed you some three-dimensional visualization of this light path, and then we have done a scanning procedure. We have regarded the three-dimensional law of reflection, and now you can see this the spots are now equidistant on our screen. Now the next example I want to show you is a dual axis scanning setup like the galvanometer scanner you have seen in the introduction, and additionally we equip this system with an aspherical lens as scanning optic. And I will show you again the visualization of this light path first, and then we are going to do a performance analysis of the system and determine the field curvature and distortion. And for further information, please check the application example laser scanning systems #1 on our website. There you can find further information about this setup. So what we want to discuss is first the ray tracing system analysis, then I will show you how to calculate field curvature of the system and the distortion, and then we want to calculate the field distribution, especially for off-axis beams. Here's a sketch of the system we want to investigate. We have these two scanning mirrors which are tilted along two axes, and they modeling this galvanometer scanner. And here's this spherical lens. Now jump right back to VirtualLab. We're closing all the windows by using the window close all button. No, we don't want to save this, and load the next example. And here you can find now again our light source, and here we have now two scanning mirrors, and after the two scanning mirrors we have this aspherical lens. And for the positioning of this two mirrors I want to show you the slide, and we have now this dual axis assembly with the two separated mirrors, and the first mirror, the scanning mirror X, realizes the scanning process in X direction, so it needs to be rotated about the Y axis. And the second mirror realizes the scanning in Y direction, and therefore it has to be rotated along the X axis. And we have realized this in this example by using the so-called sequence of axis rotation angle definition of VirtualLab. So we can choose the rotation axis. In this case we use the Y-axis as rotation axis for the first angle. We again use the basal positioning to configure the initial setup, and later we will use the isolate positioning for the scanning procedure. And the same for the second mirror, but in this case we use the X-axis for the rotation. And here you can see the used spherical lens. This is a so-called optical interface sequence where you can enter different optical interfaces like conical, cylindrical, spherical, and so on. And here we have a spherical lens from Aberration. This is a company which fabricates such lenses, and you find additional selected components in our components catalog. Just go to catalogs, components, and then the LightTrans VirtualLab component catalog opens, and here you find some selected components, for example, hexagons and spherical lenses, and just go to low NA, and here you find the used spherical lens. And you can see a three-dimensional view of this lens. Okay, and now we're going to do a ray tracing system analyzation again to create this three-dimensional view. And again, for the initial setup, we hit the screen right in the middle, and here you can see again the light source and the two scanning mirrors and the spherical lens. So, and now we want to do the analysis of the system performance, and this performance is determined by the system's characteristics, by the so-called field curvature and the distortion, which can be measured during a one-dimensional scanning process along the scanning angle, which is called theta in this example. Now, the field curvature means that we want to detect the z distance between the detector plane and the real focal surface. And for off-axis beams, the focal plane is not equal to this detector plane, and this distance describes the so-called field curvature. And this defocusing is a very important criteria for the system performance of such a laser scanning system. And then we want to determine the distortion, and the distortion describes this x distance and describes the influence of the aberration which is caused by the scanning optic, and measure the linearity of the scanning angle, and this by spot position, which is influenced by the aberration of the scanning objective. And additionally, the field curvature is measured along the z-axis. I already told this, but it's measured in two different axes, planes. And the one plane is the so-called sagittal plane, and the other plane is the so-called tangential plane. Now we want to do such a scan, and therefore we use this field curvature and distortion detector in the light path diagram. And if you go to detector function, you see this detector needs the angle theta for calculating the field curvature and distortion, and thus we are going to use the parameter coupling feature again, which now gives this angle to this detector. And inside the parameter coupling, I've defined this angle, and now we're going to vary this angle, and the tilt angle of the mirrors are set automatically. Now we're starting a new parameter run document, and now we have this global parameter above here, the scanning angle theta, and now we're going to vary this from 0 degree to 25 degree, for example in 26 steps. So we have a step size of 1 degree. Just clicking next. Next. We are again using ray tracing. Just need our field curvature and distortion detector. Next, go. And now VirtualLab sets the configuration of the light path for each of these iteration steps and calculates the desired field curvature and distortion values. And afterwards, after the calculation is finished, I want to show you how to evaluate the calculated results by using VirtualLab. And so the calculation has finished, and here we find the so-called deviations in Z direction, and these two curves represent the field curvature for the two planes I was talking about. And for a better way of comparison, you can now combine these two graphs by clicking manipulation, add subsets, append subsets, and now you can put these two graphs into one diagram. And now clicking view and starting the multi-graph mode, and here you have both curves in one diagram. Now the legend is a little bit disturbing, so we're going to property browser, legend alignment, and put it in the left lower corner, and you can see both curves. And as you can see, the field curvature is about the half for one plane, it's the sagittal plane, and the field curvature for the tangential plane is much larger for this example. And the same thing we can do for the distortion, and this distortion is calculated regarding f theta characteristic or f tangent theta characteristic, and again we can put this in one diagram by using the manipulation setup and then starting the multi-graph mode, and you can see that the aspherical lens is better related, correlated to a f theta characteristics than to f tangent theta characteristic, and the reason for this is that an aspherical lens is partially aberration corrected compared to a spherical lens, for example. Just close this graphs, and I keep this combined graphs for comparison reason for our next example. Now, after we've performed the system performance evaluation, I want to show you how to calculate the beam profile on the target screen. And therefore we deactivate the virtual screen and activate this focal region and beam parameter detector. And this focal region detector allows us to evaluate the beam profile in the detector on the detector screen, and at the same time also calculates us the beam parameters. And the only thing we have to do is to change the simulation engine from ray tracing to field tracing, geometric field tracing in this case, and just click go. And now we can calculate the on-axis beam profile, and what we get is the field directly behind our aspherical lens and the field distribution in our focal plane, in our detector plane. And this is the spot, and we can do some interpolation and change to a false color scaling, and we can also output this is the amplitude of the EX component of the field, and we also can get the squared amplitude, or looking at the phase, and this phase is nearly flat, so we are very near to the real focal plane. And if we go to the detector results here below, we can find the calculated beam parameters, and you can see the beam has a radius of about 34 micron. And we can also do this for an off-axis beam, and therefore I load this example and we just click go. We again using geometric field tracing, and we are now calculating an off-axis beam for a tilt of, can have a look, 25 degrees scanning angle, and you can see the field directly behind the spherical lens, and here you see the field distribution in the detector plane. And what we can see now is that this beam is very strong affected by the aspherical by astigmatism, which is caused by the scanning objective. And you can see in the beam parameters, you can see the radius in y direction is larger than 200 micron, and also in x direction we have an increased beam radius, which is caused by the fact that the detector plane is not equal to the focal plane for f-axis beams. Now for this example, we have done a scan along the y-axis and evaluated the field curvature and distortion for this example, and we've also calculated the intensity and the field distribution on the detector plane. And in the next example, we're using the same system, but now we're exchanging the spherical lens by a complicated or more complex f-theta objective. And we're doing again first a three-dimensional system analysis, and then we want to evaluate the system performance again and compare it to the system with a simple spherical lens, and we also want to calculate the beam profile in the detector plane. So let's jump back to VirtualLab. We're loading this example here, and you see we have again the same configuration using the Gaussian wave light source. We have the two scanning mirrors, and just instead of the spherical lens we now use this f-theta objective. You can just double click it, and here you can see an optical interface sequence where some conical interfaces are set, and in between there's some material NPK7 glass from shot, and by clicking this three-dimensional view button you get a three-dimensional view of our lens system. Okay, so we can do a three-dimensional ray tracing system analysis again, and you see that for our initial setup the beam is again focused on the center position of the screen. And now we want to do again the system analysis, and therefore we're doing a scan again, a parameter run, and scan along the y-axis. Oh, I forgot to activate, we again need the parameter coupling. New parameter run, okay. And now we are scanning in the y direction from 0 to 25 millimeters. In this case we are scanning directly at the positions on the detector plane. Again we're using 26 steps, so we have a step size of 1 millimeter, next, and we're choosing again the field curvature and distortion detector, and ray tracing as simulation engine, clicking next and click go. And we're now scanning in millimeters because the parameter coupling for this setup already corrects the nonlinearity of the tilting process of the mirrors. And this is, for this setup it's rather simple because the f-theta objective has a fixed relation between the scanning position on the screen and its focal length and the scanning angle, and that's why it's called f-theta objective. And the calculation is already finished, and we can again get the output for the graphs for the field curvature, and we're going to put them in the same diagram again. I'm clicking a little bit faster because you already know how this works. And here we get the combined output for the field curvature, and now we can load we open the example from the spherical setup with the spherical lens, and here you can see that if you look at the scale, that the field curvature is much smaller for this f-theta objective than for the setup with the spherical lens in both planes. And for the f-tangent theta and the f-theta distortion we can do the same. just combine the two outputs. Okay, and activate the multigraph mode and put the digit down here. So, and we can reopen the example file from the first system. And here you can see now that the f theta distortion for the system using the f theta objective is very, very small. And this shows us that this f theta objective shows a good exhibits in good performance. And also the f tangent theta distortion is smaller than for this spherical lens. So this system has an overall better performance than the system with a simple spherical lens. And now we're going to calculate the spot on the detector plane, and therefore we first go to the center position, we enter the position 0, 0, and yeah, we can also editing the values of the parameter coupling by going to the parameter overview here, and okay, so this also edits the settings of the parameter coupling, and we're choosing again the focal region and beam parameter detector and deactivating the virtual screen and changing the simulation engine to geometric field tracing, click and go. And now we're going to calculate the spot for on-axis beam, and again we're getting the field here in the on the focal plane, and we're getting this nice round shaped spot. And then we want to calculate the off-axis beam. I've prepared the setup and just click next. And we calculate this now again for a position of 25 millimeters. And as you can see, for this setup, the beam, the scanned beam, the off-axis beam, has almost a round shape too. And if you look at the beam parameters, which are calculated at the same time, can just swap. So here you can find the beam parameters for the off-axis beam, and here you find the beam radius for the on-axis beam. So it's almost the same shape. And this is the characteristic of this f theta lens objective. And what we've seen in this example is now that we've calculated the field curvature and the distortion, and the field curvature is much smaller than for the first example with the spherical lens, and also the distortion is much better, and the calculated focal spot for off-axis beams is doesn't show this strong astigmatism than for the first example. So let's go to the next example, and now we are going to the micro mirror setup again, and now we want to investigate the beam quality and the beam shape in the detector plane if the scanning mirror has some deviations and aberrations. And this is of interest because if the mirror is has a glass substrate and is just coated with silver, like in the dual scanning setup, you can polish the glass and then just coat it with silver, and this mirror has nearly no aberrations. But if you're fabricating a micro mirror, you have just a thin metal plate, and during the fabrication process it could be bended a little bit, and during the dynamic scanning process it could bend it a little bit more, and this causes some surface deviations of the mirror and affects the spot quality. And what we want to do now is to introduce some different aberrations which are represented by Zernike polynomials, and then calculate the effect on the beam shape in the detector plane. And I close all the windows we used before by using the close window button again and load the example. And here you can see the two scanning mirrors. And for the scanning mirror, we now don't use a plane interface, but we use this Zernike interface. And here you can enter all the coefficients for the Zernike polynomials. And with the help of these polynomials, any arbitrary phase of surface deviation can be fitted and represented. And these polynomials are classified by their coefficients, and they are expressing the polynomial and the radial factorized order of this polynomial. And yeah, these are different terms, and I choose, for the first example, I choose the coma polynomial, and I configured the setup in that way that the aberration of the mirror has a peak value of about 1 wavelength. And in the scaling options, you can scale this a little bit. So for the first example, we are reducing the aberration to near 0, and I calculate the spot for a nearly non-aberrated system. And now we're using the classic field tracing engine to calculate the spot shape in the detector screen, and you can see for a non-aberrated system we're getting this nice round shape again. And now we're going back to the scanning mirror and increase the scaling to a value of 1 and doing this calculation again. And now we can see the influence on the spot shape for a deviation of the mirror peak value of 1 wavelength. And the calculation again needs some time. So it's finished, and if we go to the false color scale, you can see the maximum of the spot is shifted a little bit in the y direction. And if you further increase this aberration, this effect is increased either, for example, for a scale for 5, about 5 wavelengths aberration. The spot shape is varied much more and shows a very asymmetrical shape. You can see here. And if you would do a beam parameter analysis of this beam, you would see that, for example, the m² value is now very, very high for this example. And what I forgot to mention is if you're going to the scanning mirror and to the surface, and we enter here a little bit larger scaling, you can also visualize this bending of the surface. Just go to the 3D button here, and you get a 3-dimensional view of the surface. Okay. So I want to show you another aberration. It's called so-called trefoil aberration, and it's a symmetrical aberration. And again, we have a scaling in a magnitude of 1 wavelength. So we have a peak value deviation in this magnitude. And again, we are going to calculate the spot profile on the virtual screen, on the target screen. And what we get now is a symmetrically aberrated spot, and this trefoil aberration leads to a triangular shape of our spot. And if this is further increased, we get spot shapes like this. Because we run a lot of time, I will show this on the slide. We've seen for a peak value of about 1 wavelength, we have this spot shape on the left. And if you further increase the deviation of the mirror, the spot is gets more and more affected. So you can also do a whole scan with these aberrations, And in case of static aberration, it would mean that the deviations are constant for all deflection angles. You just can do a parameter run and create such a scan pattern you can see below. And for example, for the coma aberration, you get this pattern, and for a trefoil aberration, you get this scan pattern. Here you can see the aberrations does not change during the scanning process. And if you have more complex mirror aberrations, you can again use the scenic interface to assume these aberrations, because with the help of the scenic key polynomials, nearly every type of aberration can be fitted. And another possibility is to use a combined interface, and this interface allows us to combine two or more different types of aberrations and use two or more interfaces which are merged to fit these aberrations. Again, we can also use scenic type interfaces, and the reason why I use this combined interface is that by using this combined interface we can now investigate the influence we get by static and dynamic aberrations. Static and dynamic aberrations mean that we have the bend. The static aberrations are the aberrations we get from the initial bending of the mirror, and the dynamic aberrations occur if the mirror is scanned and is bended by the scanning process. But doing a static combination first, you can see here we have this combined shape, and if you look at the beam in the target plane, you see this triangular shape from the trefoil aberration, and the maximum is shifted a little bit downwards, so you see the effect from both aberration types. And now we can do a scan and regarding the static and dynamic mirror aberrations. And in this example we assume that the second aberration, the trefoil aberration, is related to the scanning tilt of the mirror, and its strength is increased if the tilt angle is increased, and therefore we can see that the scanning, the spot for the center position, for the center scanning position, is dominated by the coma-shaped aberration, whereas the scanning positions at the for larger tilt angles is dominated by this trefoil-shaped aberration. And this means that with the help of VirtualLab we can investigate the influence caused by mirror aberrations, and also which effect these aberrations have if we do a full scan procedure, and we also can calculate the influence of static and dynamic aberration terms. And the last example I want to show you is the more complex setup, where we have a laser scanning system, and what we want to investigate is if we are scanning at a beam diffuser which creates an eye box for our eye, and we then investigate this with a model of a human eye. We want to calculate how the spot shape on the human retina is. And therefore we're using again a single scanning mirror setup, which is based on a micro electromechanical system. We have one scanning mirror. We have additionally an imaging lens which focuses our light on the beam diffuser. The beam diffuser creates the eye box we want to observe then, and we have a collimation lens. And then the model of the human eye is consists of a pupil and a lens model, and the virtual screen now is the human retina. And I've opened this example, and due to the fact that this example is a little bit complex, the calculation needs some time, about 3 minutes. And I started the simulation, and I will load this example in another VirtualLab So I can show you the imaging lens. The imaging lens is just a spherical lens, as you can see here, and focuses the light on the diffusing element, which is just a diffractive element. You can show here diffractive phase-only element, and creates now an eye box for our investigations. Here we have the collimation lens, which is again a spherical lens. And here in the end we have the model of our human eye. Here is the model of the lens. And now we're calculating the spot on the retina for the on-axis beam. You can have a look. It's not finished yet. So we jump back to PowerPoint, and you see we will get this beam shape for on-axis beam, and as you can see the beam diameter is about 10 to 20 micron, and this is in the same order of size than the sensitive structures on the retina are. So this spot can be seen by the eye, and if you're doing some scanning, some off-axis beam, the shape is a little bit varying, but due to the fact that this spot is very small, this variation cannot be seen by the eye. And if you're now doing a scanning procedure for an equidistant grid, we're getting this intensity distribution. If we are scanning on an equidistant grid, I would expect first that we get an equidistant spot pattern on the retina, but this is not the fact. And this effect is called the speckle generation, and we're getting this non-uniform intensity distribution, and this has to be regarded if you want to realize a high-performance imaging system. And for this purpose you have to decrease this speckle pattern generation, and this can be done by using VirtualLab. You can simulate the whole setup and optimize the setup to reduce this variation of the intensity on the human retina. And now we're at the end of this webinar. I've shown you how to simulate different laser scanning systems with different scanning objectives in VirtualLab, and I explained how to use the different light propagation techniques and what the benefits of these light propagation techniques like ray tracing and physical optics propagations are. I gave you some insights into the positioning system of VirtualLab, which ensures rather simple realization of these laser scanning setups in case of, for example, single and dual axis mirror setups. And we used a combination of the tools which are implemented in VirtualLab, for example, the parameter coupling feature and the parameter run feature, in order to evaluate your system, the system performance, calculate the field curvature, and so on. And I also discussed the possibility to evaluate the calculated results inside VirtualLab. So thank you for your attention, and do not hesitate if you have further questions. Thank you.